In 2018, a small team at the Allen Institute for AI released a model where the vector for bank depended on the sentence around it. Same word, different context, different vector. Every major NLP benchmark record fell within weeks. Glue, Squad, Coreference, Sentiment, all of them, in one paper, in one release. This is ELMo, embeddings from language models. The moment word vectors became contextual, and the direct bridge from static embeddings to BERT and GPT, and every modern language model. Peters and colleagues 2018, the paper that ended one era and started another. Last video I showed you the polysemy problem. Bank had 10 meanings. Word2Vec squashed them into one muddy gray average. Every search engine and every classifier built on static embeddings inherited that blur. WordSense disambiguation had spent 60 years trying to fix it, stalled at 75%. NLP just sort of accepted this. Until the puzzle for today. Static embeddings gave you one vector per word. That was the whole design. If you change the design so the vector depends on the sentence, does everything just work? Or does it break some other property we cared about? In 2018, Peters and colleagues answered that question, and the answer surprised the whole field. Today's 3 beats. First, what ELMo actually is. Language models as embedding sources, the core mechanism. Second, the biLSTM under the hood, bidirectional, sentence level, where the context comes from. Third, the benchmark earthquake, and the bridge to BERT, GPT, and transformers, which is lecture 6. Beat 1. What ELMo does. Simplest possible framing. In Word2Vec, you have a lookup table. Word goes in, vector comes out, fixed forever. In ELMo, you have a language model. A whole sentence goes in. For each word in that sentence, a vector comes out. And that vector depends on all the other words in the sentence. Concretely, take bank. In the sentence, I sat on the riverbank fishing. ELMo outputs a vector that's near waiter, shore, grass. In the sentence, I went to the bank to deposit a check. ELMo outputs a different vector, near money, teller, loan. Same input word, 2 clean, separated vectors. The polysemy problem from last video, dissolved. The name, ELMo. Embeddings from language models. Because the vectors come out of a model that was trained to predict the next word. That's it. That's the whole trick. If you train a strong enough language model, its internal representations of each word already know a lot about the surrounding sentence. You just extract those internal states and call them your embeddings. Beat 2. The mechanism. Under the hood, ELMo is a bidirectional LSTM, 2-part name. LSTM. A specific kind of recurrent neural network that reads a sequence one step at a time. Bidirectional, it reads the sentence forward and backward, then combines both directions at each word. So the vector for bank sees the words before it and the words after it. Full context, both sides. One more nuance. ELMo doesn't just take the top LSTM layer, it takes all the layers and weights them. Lower layers of the biLSTM tend to capture syntactic information, parts of speech, morphology. Higher layers tend to capture semantic information, meaning, sense. ELMo combines all of them, which turns out to matter. Different downstream tasks care about different layers. How you use ELMo in practice. You take an existing NLP model, a sentiment classifier, a question answering system, whatever. Wherever your model would have looked up a Word2Vec vector, you instead call ELMo on the full sentence and get a contextual vector. Same interface, different quality, drop-in replacement, and the field was ready. Beat 3. The benchmark earthquake. Paper drops in February 2018. Every major NLP benchmark. Squad. Question answering. Plus 4.7 points. SNLI, Natural Language Inference, plus 0.7. Coreference Resolution, plus 3.2. Named Entity Recognition, plus 2.1. Sentiment Analysis, plus 2.9. Textual Entailment, plus 1.4. 6 state-of-the-art results. 1 paper. Why did this hit so hard? Because every one of those benchmarks had been improving by tiny fractions of a point per year. Then ELMo showed up and moved several of them by multiple points, overnight. And critically, it did that by changing the embedding layer only. The models on top didn't change. That meant every existing NLP system could benefit. every lab, every product team. And here's the deep point. ELMo proved that contextual embeddings beat static ones on basically every task. Within 9 months, Google released BERT, which did the same thing but with transformers instead of LSTMs, which was better. And within another year, GPT. Same core idea, context in, vector out. Every modern language model is a descendant of the ELMo bet, which is where Lecture 6 picks up. 3 takeaways before the quiz. 1. ELMo. Sentence in, contextual vectors out. Same word gets a different vector depending on the sentence. Polysemy problem solved. 2. Under the hood, a biLSTM language model. Read forward, read backward, concatenate, weight all layers, extract as embeddings. 3. Every major NLP benchmark fell in weeks because ELMo was drop-in, and 9 months later, BERT and GPT proved contextual embeddings were the new default, forever. Quiz 1. What's the core difference between Word2Vec and ELMo? A ELMo runs on GPUs. B. Word2Vec gives one vector per word. ELMo gives a different vector per sentence context. C. Word2Vec is faster. Or D. ELMo has more parameters. B. The interface changed. Word2Vec is a lookup table. Word in, one fixed vector out. ELMo is a language model. Sentence in, one contextual vector per word out. Same word gets different vectors in different sentences. Polysemy. Dissolved. That's the whole game. Quiz 2. What architecture is ELMo built on? A transformer. B. A bidirectional LSTM language model with weighted layer combination. C. A convolutional network. Or D. A support vector machine. B. biLSTM. Forward pass reads the sentence left to right. Backward pass reads right to left. Concatenate at each token. Then weight all the layers together, because lower layers carry syntax and higher layers carry semantics, and different tasks want different mixes. Note, transformers came later, BERT and GPT, 9 months after ELMo. Quiz 3. Why did ELMo hit so hard so fast? A open source. B. It was drop-in. Replace the embedding layer of any existing model and instantly get better results across every benchmark. C. Marketing. Or D. Faster than Word2Vec. B. Drop-in. That's the whole story. Every NLP team already had a working pipeline. ELMo just swapped the embedding lookup for a sentence-aware version. Same rest of the model. Better inputs. Multi-point gains across 6 benchmarks in Table 1. Within 9 months, BERT and GPT arrived, and contextual embeddings became the new default, forever. Back to the puzzle. Static embeddings had a polysemy ceiling. ELMo blew through it by making the vector depend on the sentence. And within a year, BERT and GPT took the same idea into transformers and never looked back. That's the modern era. Everything after 2018 is descended from this move. But before we jump to Lecture 6, one more thing. How do you actually measure whether embeddings are good? Next video. Next time, evaluating word embeddings. The analogy task. Google's famous dataset. Linzen's 2016 critique of the whole benchmark. Vector space biases. And why good embeddings is a task-dependent question. Hit subscribe.